And thank you for joining Aqua Security today as we explore security risks and tactics for securing the software supply chain. And we'll discuss why cloud-native applications require a somewhat different approach. To begin, I'd like to just kind of level set on the technology landscape. In recent years, we've seen an explosive growth in terms of containers and Kubernetes, serverless functions, other cloud-native technologies, and most notably in production environments. Now, if we're applying statistics, you're probably using some or all of these technologies in production yourselves. And if you're not currently, it's a safe bet that there's probably an initiative growing somewhere in your organization to do something like this in your near future. So looking at data from a 2020 CNCF survey, we've seen a huge shift in terms of companies who were testing cloud-native technologies in staging and have now switched to using them in production in their public and hybrid cloud environments. Now, what do security professionals think of this shift? CyberEdge actually did a survey asking participants to rate their organization's overall security posture and their ability to defend against cyber threats. The results here show that security professionals believe that containers and cloud-native categorically is it's an area where they feel that they are ill-equipped with what they need, maybe lacking things like clearly defined best practices or technologies and the processes that are necessary to improve or really even to maintain their security risk posture. And if you talk to DevOps professionals, they've come to the same conclusion. One of their largest hurdles when trying to move these cloud-native applications into production is that it's that typical opposition, that dichotomy between security and DevOps teams when it comes to that balance between speed and security. Usually this is the result of force-fitting legacy security programs or slightly modified versions of these legacy security programs, force-fitting them into new cloud-native ecosystems built on agile DevOps and CI/CD methodologies. Regardless of who you talk to and whether their focus is security or DevOps, security for cloud-native apps and the environment where they get deployed it's both a headache and a mystery for really the plurality of organizations today. When we use terms like cloud-native, what we mean is the notion that people are applying these agile DevOps or CI/CD methodologies to the software that they create and deploy. And that software is made out of many different artifacts and different layers. And that software is also designed for some sort of containerized deployment in single or multi-cloud environments. So there are a lot of moving parts in cloud native. And for most people, it's definitely worth the complexity in order to achieve the better scale and performance. It does add some additional pressure on dev teams, though, to meet the tighter software shipping deadlines and still maintain a strong security posture. And we can see in this somewhat simplified diagram that when we add the software supply chain to this conversation, vulnerabilities and malicious packages can enter anywhere in this mix of base images, infrastructure components, open source or third-party components. And yeah, developers do often decide which components go into these. This isn't always the case, though. You can think of instances like with transitive dependencies. But these libraries and packages that developers bring in are not, they're not always benign. So at the crux of this issue is the fact that software nowadays is sort of a composite creation. It's made up of bits of custom proprietary code that developers write. This used to be the largest portion of the code base, and now custom code is kind of being relegated to serving as the string that ties various software components together. And with custom code, the potential issues, they usually manifest themselves as weaknesses in code that can be used as potential attack vectors. And this is where more traditional security practices apply, like various types of application security testing. You can think along the lines of static analysis or black box testing, things like that. And this is where we see the direct impact of developers' skill and their security risk awareness. So having an experienced and informed dev team is going to help minimize the risks that get introduced in custom code here. And then we've got open source components, and these make up the largest portion on average of today's applications. Developers are using open source to accelerate development and to build on the contributions and innovations of that broader open source community. The risk here comes in the form of vulnerabilities that are baked into the components themselves. And there's thousands of vulnerabilities discovered every year. There were, I think, more than 14,000 published last year alone, and that's just looking at the CVEs. We're seeing this increased adoption of things like software composition analysis, or SCA, you may have heard that term, which identifies open source components and applications or containers, and then it documents any associated vulnerabilities into kind of a software bill of materials. Security and dev teams take this output, they do a little bit of triage against the hundreds or thousands of issues that are discovered, and then they use information from resources like the NVD or vendor security advisories to upgrade or patch the vulnerabilities. Now, the success of these remediation techniques usually depends on the availability of a patched version of that component. And without a patch, most organizations will usually require some sort of mitigating factors or compensating controls to be put in place. Then we see third-party software being brought in, and this can be compiled binaries, third-party packages, commercial software, contractor deliverables, things like that. And in any case, the software is, it's usually largely out of an organization's sphere of influence when we talk about security. With these, you just tend to lack access to the source or have limited control over risk remediation. So much of the security preparations made to address these risks depend on the third party notifying people about the security risk and providing remediation guidance or a solution to resolve it. Now, something a lot of people tend to overlook is how much trust is employed as a security measure with third-party software. There's a tendency to sort of lean on SLAs and excuse me. There's a tendency to sort of lean on SLAs and pardon me. And in expectations that software vendor is taking appropriate steps to secure the deliverables that you're consuming. And this kind of inherently requires that the software vendor is effective at securing these first two boxes that you see here on the left, and that they have established processes for addressing any new risks that come up, because this all has a cascading effect to anyone that they provide software to. But there's also this growing risk today of there being hidden malicious packages in the software that you create and consume as part of your supply chain. And this can come in by any way of these previous three avenues that you see here. Most commonly, we see open source or third-party software being the main entry point for these malicious packages, but there's a wide variety of potential entry points, and we'll discuss those more in depth a little bit later. And historically, a lot of organizations try to maintain a blacklist of specific packages that they forbid developers from including in their projects. But if any of these security measures fail to detect malicious packages, and most of them do fail at this detection, then the default security measure is to try to get evidence of an attack, to view those indicators of compromise, usually only after the software has been put into production. And so if you think back to that layered cloud native architecture that we just saw, there are a lot of opportunities for malicious packages to be introduced into what you put into production. And at that point, it's just too late to implement any of these security practices. And even then, the complexity of attacks that we've seen over the last few years it's grown considerably beyond what can really be addressed by any array of what you see here in terms of security practices. In 2019, we often saw a lot of these linear attacks trying to do something basic. In this example, the goal was crypto mining. And then they evolved to not only achieve that linear goal, but then to open doors to new activities and new malicious goals. And then they evolved again, this time to kind of expand their influence and facilitate those malicious attacks at scale. And now we've got multiple layers of complexity with multiple goals, multiple phases of an attack, and a bunch of challenges presented to security teams, to DevOps teams, and to developers. Everyone here has some responsibility for securing cloud-native applications in the face of this, this sophisticated enemy. And now there's some interesting things that we start to find when we analyze these types of supply chain attacks from a macro level. Aqua Cybersecurity research team, they go by the name Team Nautilus. They publish an annual report where they examine advanced threats to cloud-native applications and environments. And Aqua's research, as well as many third-party security reports, have all found an increase in the complexity of attacks that target containers and Kubernetes. These are kind of two of the most common and fundamental aspects of a cloud-native initiative. And research shows that these attackers can find and attack vulnerable hosts within 5 hours on average. These attacks are avoiding detection. They're making use of those multiple layers of complexity that we just saw for cloud-native ecosystems. And they're getting better at maintaining persistency for sustained attacks. And they're using configuration errors and container architectures to escalate privilege so that they can advance their attacks. And a lot of times, as we just saw, these attacks have multi-level impacts and perform multiple malicious activities that really make it hard to pinpoint the exact vector or the exact malicious package. And all of this illustrates the idea that as cloud native becomes more commonplace, the attack landscape's evolving with it, and security has to keep up. So a lot of these attacks use some similar basic principles and target organizations that may lack the experience or the means to preclude them. These supply chain attacks tend to rely on exploiting developers' oversights in coding, maybe oversights in build automation, configuration errors, inadequate security at runtime. And now there's a wildly diverse range of these attacks. But we do see a surprisingly high popularity of some of these examples that I've included on the right for you. You know, typo squatting, you may have heard of this. Typo squatting is basically a tactic of naming malicious files with various misspellings of popular libraries. So one example of this is the Jellyfish library, which used a misspelled version of the popular Jellyfish library, where they replaced that first L with a capital letter I. And at the time of discovery, this malicious package had been available for a year, and it had become associated with another popular PyPy library, which then became malicious by association. And so that then extended that scope of malicious influence. And these things are really easy to overlook when a developer is trying to kind of quickly search and incorporate a component into their project on these tight deadlines. You've got dependency confusion. This is actually a really interesting approach that kind of came into vogue earlier in 2021 with Alex Berson's research that was published in February. And Alex attempted to find private library names, like in JavaScript files or GitHub code, for example, and create his own public libraries that match those private library names. And so basically from this research, it's been proven that automated build processes would often pull public libraries from places like NPM or PyPy instead of from private repos. So you can see the opportunity to incorporate malicious packages that way. And then there's this broader concept of exploiting trust. And this manifests itself in a lot of different ways. We've got examples of libraries being altered to include malware when a malicious developer volunteers to take over the project, for example. We've seen malicious actors use bots to artificially inflate the ratings and stats of malicious packages to entice or encourage developers to trust that library as they're searching for components to pull in. And we've got many highly publicized examples of compromised software vendors. One really good example of this was actually just disclosed in April of 2021 when CodeCov announced that someone had used an error in their Docker image creation process to extract credentials and modify their bash uploader script. And that then allowed them to ultimately export information from CodeCov's users and customers and sent that then to a third-party server. So these types of attacks, these multi-level sophisticated attacks, they can't be detected with application security testing or software composition analysis. Malware isn't a vulnerability. These things only manifest at runtime. So how do we do this safely? How do we detect these safely? Well, we kind of talk through this a few recommendations that we make to people who are tackling this modernization strategy, whether they're starting by containerizing applications, maybe they're employing more advanced DevOps methodologies or pursuing a full shift to cloud native. First, it's important to empower and educate DevOps teams while fostering a DevSecOps culture. You can maybe think of this as a version of that infinity loop diagram that's commonly used to represent DevOps and DevSecOps. You might have heard this described as shifting security left. The point here basically encompasses the idea of identifying barriers to performance, baking security into established workflows, and getting that security risk information directly into the hands and the tools of people who need it to do something about it. And so then this includes aspects of our second point, automating and embedding security controls into the CI pipeline. A lot of people tend to think of this as a goal or an end result, but really it's a deliberate process. It doesn't just happen by changing a setting in some of the tools that your dev teams or security teams or DevOps teams are using. A lot of security professionals do express some concern about automation. You may be perhaps one of them. Usually when they think about how to achieve this step, and a lot of times this concern is mostly around sacrificing control. But these two ideas, security and automation, actually they work in concert. Proper policies and controls actually facilitate that secure automation. And then automation is critical to scaling that control and compliance to keep up with these faster shipping cycles that we have in DevOps. So the success of this second stage is largely influenced by the efficacy then of our next and third step. Establishing risk tolerance and security standards for the supply chain. This is partly those policies, partly security risk detection. There's elements of prioritization and triage in there, and those all influence your ability to find and fix risks before they become issues in production. So, to do this, I always recommend that you ask things like, what's the review process for risks in code versus risks that enter through the supply chain? Which response steps happen automatically? Who gets notified? The answer to those questions may involve people outside your team or even outside your organization. So it's important that your risk tolerance reflect that. And with this in mind, your risk tolerance and your security standards for supply chain packages will probably differ from what you have for custom code, for example. And like we discussed earlier, malicious packages aren't vulnerabilities, and so they shouldn't always be evaluated or treated like they are. And again, just remember that remediation in the context of the artifacts that get ingested through the software supply chain, they may not always be a task that your developers can even achieve. Issue resolution might only come as the result of a longer process of notifying a vendor that there's an issue, and it may be subject to their SLAs for response, for example. So your evaluation and prioritization of these risks should reflect this extended complexity. And lastly, eliminate trust from the security strategy. You might recall in the last slide that I covered some examples of how trust is being used as an attack vector or an entry point for exploitation. You can totally provide vulnerability information to your developers and integrate security testing everywhere. But the software supply chain introduces a lot of additional potential points of failure when those security procedures might not even be invoked and they might be ineffective. So approach this with caution, or maybe think of it like this, like a trusted vendor may not approach software security with the same rigor and standards that you ascribe to your own internal security or DevOps or dev teams. So you don't want your success or failure to depend on the security adequacy of someone else. And your cloud native security toolkit and DevSecOps processes, they need to reflect this. So how do these 4 stages, these best practices coalesce into a solution to address security risks in a cloud native supply chain? Well, basically, it ultimately means that you need to expand your security approach to include these types of sophisticated attacks so that you can actually trace and visualize the attack kill chain before an attack is actually carried out. And like we talked about already, this is going to require running the software. Now, of course, you don't want the first time you do this to be in production. So run the containers in a secure sandbox environment and be certain that you have a security solution ready to go to identify and track malicious behaviors that only manifest themselves in runtime. The malicious or the anomalous activity that you detect should then trigger precautionary measures to either block the malicious artifacts from being deployed into production and kind of start that cascade of notification and response. I always recommend to automate this as part of the build process or part of the CI/CD pipeline, just like we outlined in the best practices. That way, everything's being tested in pre-production without adding hurdles for your security or your DevOps teams. So what you'll end up doing is actually carrying out your standard workflows, and then you'll get this detailed report at the end, and then you can make sure that the results of that analysis get shared with anyone who needs that insight to take appropriate action. And again, in keeping with these best practices, be sure that whatever security solution you implement, for this can make sure that it can support policies. That's going to facilitate that automation requirement and still give you that control over your security risk posture. And remember, like I said before, the standards and risk tolerances that you bake into your policies, they may be different from those that you have for traditional vulnerabilities, maybe just due to that lack of control over the remediation of risk, for example. And so you should be examining all the behaviors and actions that occur when the application's running in that pre-production sandbox. Identify all those indicators of compromise, all those kill chain activities. I've given some examples here. And anything being used in the container is going to have some sort of behavior. And that behavior might be malicious. That's just an inherent risk of today's software supply chain. So at the end of the day, the attacker's trying to do something. And if you're waiting in those places to observe it, to analyze and to document it, you've got a chance of finding it and fixing it before it can do any harm in production. And then lastly, support SecOps and forensics by automatically classifying those detected behaviors by standards like maybe the MITRE ATT&CK framework. This is going to kind of help you assimilate that insight that you gather into the greater story of your organization's security risk posture, so that you're not comparing, say, apples to oranges when your security team looks at the risk profiles of your cloud native apps and legacy apps and internal software and commercial technologies, when they look at all of that in aggregate. And so including an automated mechanism like this, and for our discussion today, I'll reference Aqua's dynamic threat analysis that sort of applies these best practices that we just covered into this 5-phase approach that you see here. incorporating something like Aqua DTA into your cloud native security strategy is going to help you reduce your exposure to supply chain risks without adding that additional burden on your security or your DevOps teams. This approach is going to help avoid surprises for your ops teams who need to attest to the security of the software in production. It helps satisfy security teams' needs to fully evaluate risk. And it's going to allay some of those concerns that developers might have when sourcing third-party or vendor-supplied packages. And it's a really impactful way to support forensics requirements and compliance standards. So I'll just end with a quick example of how an organization that we worked with kind of baked this dynamic threat analysis in and some of the other tools for vulnerability management and policy enforcement so that they could really take control of their cloud native software supply chain. As we look along this linear representation of their CI/CD process, we kind of see that first, they set this goal to shift security as far left as possible, trying to deliver that security risk information and remediation guidance directly to developers for faster issue resolution. And then they integrated security scans into their CI/CD pipelines. They automatically did vulnerability scans at build, and they checked for compliance against the assurance policies that they put together. And this kind of gave their security teams that automated control that we talked about earlier, so that everything that passed through build underwent a thorough analysis. And if the images and artifacts complied with policies, they would push the images into their pipeline. And if not, the process could be blocked, and they configured alerts and notifications. And all this was defined based on various contextual factors, of course, but it did help that sort of fail fast idea that's popular among DevOps. And then they would have similar security practices integrated and automated with their registries, their container registries. And so this helped to establish a standard of security regardless of how an artifact entered the registry. We know that not everything passes through a standard build process before getting checked into a registry. So this was a crucial step for them, giving them, given the variety of tools and processes that they used, not only across their different dev teams at their organization, but also across the software suppliers that they had as part of that supply chain. So again, here they would do security scans, manage vulnerabilities, and verify compliance with those security policies. And then as a final control gate before deployment, they sandbox their images using that dynamic threat analysis that I mentioned, so that they could identify any malicious packages that were, inevitably undetectable to previous scans. If you think back to some of the limitations of those various application security testing and SCA technologies we talked through, and now consider also that helpful mnemonic that I shared with you, that malware is not a vulnerability. So this gave them automated and secure detection capabilities of malicious or non-compliant behavior that occurred only during runtime. And it was important to them that they automate a series of actions for faster response and more consistent security. So they established policies for enforcement against these DTA results and blocked promotion or deployment upon policy failure. They documented the whole kill chain and all the activities that fed into their incident response and forensics workflows. And so then dev teams could then be more informed so that they could accelerate that remediation based on those results. And now I do want to clarify, all this didn't necessarily make their supply chain more secure, because again, part of the supply chain itself means that there's an element of control that gets sacrificed. But they had a consistent and reliable way to take control back before production and uphold their own standards for security. So the nice thing about this, with these various tests and controls baked into CI/CD pipelines, this happens automatically every time there's a code change. And it establishes security resilience within that software supply chain, because it scrutinizes the third-party and vendor supplied packages against internal standards for, security risk tolerance and compliance. And really, this is kind of a nice at-a-glance representation of what it looks like to roll all of those best practices and supply chain security into a secure cloud-native workflow. So in closing, thanks for joining me today to kind of talk through some supply chain risks that are really inherent to today's cloud-native software landscape. If you'd like any more information on how to secure this software supply chain or just cloud-native security in general, of course, you can always visit aquasec.com, and you can check out a lot of interesting cybersecurity research that Aqua's research team is doing, including that annual threat report that I mentioned earlier. And check out Aqua's GitHub. Try out a variety of different open source tools, that are supported and maintained by Aqua, for cloud native security, vulnerability scanning, and cloud infrastructure security, all that fun stuff. So, thank you very much, and I'm happy to take some questions.